Okay, good morning. All right. Okay, today we're going to look at section 14.4. We'll look at tangent planes and linear approximation. Okay, you look at linear approximation back when you took Calculus 1. So let's do a very, very quick review of what you did back then. Again, we're going to use the knowledge you have from one variable case and then extend it to two variable and beyond. Now you might remember that in a one variable case, if you had some function, y is equal to f of x. And you choose some point on this curve, let's say right here, where x is equal to a and y is equal to f of a. We know how to find a tangent line. And we also know how to find the equation of a line. Tangent line at a comma f of a. We'll call this tangent line equation L, capital L, function of x, right? So there's just the equation of a line in the point-slope form. Y minus a point is equal to slope times x minus some number. So that's your tangent line equation. Now, if you remember, linear approximation says that if you stay near this point, then the tangent line and the curve look about the same, right? If x is near, of course, the near, how near is depends on the function. Then the tangent line is roughly equal to the curve. So near x is equal to a, we can replace that function with the tangent line. And the advantage is you replace a complicated function with just a line, and line is very easy to deal with. Okay, you remember this stuff? Yes? Good. We'll use exactly the same idea, now extend this to a three-dimensional case. For a two-variable function, now we're in a three-dimensional world. The function is no longer just a curve. The function is now a surface. So as an example, I'm going to use a portion of a sphere to illustrate what we're doing here. Okay, so let's look at the surface here, a portion of a sphere. In the first part where x, y, z are all positive. instead of forming a tangent line at a point, we'll call that x0, y0, z0. Instead of forming a tangent line, now we're dealing with a tangent plane. Because there's an infinitely many tangent lines at any given point. If you collect all of those tangent lines together, you get a plane. So that's the tangent plane. The tangent plane contains all the tangent lines. All right, so let's say the point we're dealing with is right here. And nearby there, we can form a tangent plane, this green plane right here. Okay, so that's my tangent plane. And we can use that tangent plane very much the same way we use the tangent line. Nearby that plane, nearby this point, that sphere and the plane, if you don't move very far from this point, the sphere and the plane are about the same. For example, here on Earth, from our perspective, the Earth looks flat, right? Because we can't see very far. So imagine this is where we are. We can't see very far. So from our perspective, the Earth looks flat. We won't see the curvature until we get very high, or we move very fast, or very far away. So that's the idea here, using the tangent plane the same way we use the tangent line. Can be used to approximate the function near the point x0, y0, z0. So the first question we need to answer is, what is the equation of that tangent plane? Once we have the equation, we can deal with it the same way we use the tangent line. Okay, so that's the very first question we want to answer. Let's go back to the graph here. Now let me choose x to be a constant. If I fix x, this is the curve I get. This is the trace. Trace with x is equal to x0. A portion of that is a circle. It's a portion of a circle. And I can do the same thing with fixing y to be y0. And we're going to need those dotted lines a little bit. So first, let's write down the equation of any plane in general, any plane. The equation of any plane is some number a times x minus x0 plus some other number b times the same thing with y plus some other number c times the same thing with z equal to 0. Right? That's just for any given, any random plane. Now, do you remember what A, B, C are? What do they form? The normal vector, very good. Okay, so that's the vector that's perpendicular to that plane, and we'll call that A, B, and C. Let me rearrange this equation just a little bit. I isolated z, and now I'm going to divide it by capital C. And for simplicity, I'm going to call negative a over c lowercase a, just for simplicity. And I'm going to call capital B, negative b over c lowercase b. And now if I could figure out what lowercase a and b are, then I can find out the equation for my tangent plane. All right, so now look at this picture that we just drew earlier. The first thing I'm going to do is to look at a trace with x is equal to x0. I see this one here. Okay? From my picture, if I look at, now when I set x to be a constant, I'm looking at a curve from the YZ, on the YZ plane, and I see a portion of a circle. So this is what I see. That's that particular trace. And there's the point, x0, y0, z0. And the tangent line in this perspective, we're looking at this edge on, we just see a line, right? So this is the portion of the tangent line that we see from that perspective, tangent plane. This is the side view of tangent plane. Now it's a line, right? What is the slope of that line? That green line? Think back to what we did last time. What did we do last time? Partial derivatives. And partial derivatives always a slope. So in terms of partial derivative, what is the slope of that solid green line? What is changing here? I'm holding x constant and y is changing. So we're looking at how z is changing with respect to y. So what would that be? partial derivative, good, partial derivative of f with respect to y, right? How f, which is z in our case, is changing with respect to y. And actually, we're looking at this at a very specific point. At x is equal to x0, y is equal to y0. And this means this quantity, let me write this down here. It's a slope. Slope is the change in the height over the changing the horizontal distance, y minus y0. Right? That's a slope. Rise over run. That's just our slope. The equation in the green box, if I set x to be x0, so this is getting complicated here. Let me draw an arrow here. This equation in the green box with x equal to x0 reduces to z minus z0 equal to b times y minus y0. I dropped my mic, and I didn't mean to. I would have chosen a more dramatic moment to do the mic drop. But now the timing's all off. Anyway, we're back to what we're doing here. All right? So look at this equation here. Now with x equal to x0, this disappears. So I get this equation here. If I solve for b by dividing by y minus y0, and then compare to what we knew from earlier just by looking at the slope, this tells us that b in the equation of the tangent plane is equal to the partial derivative with respect to y at that point that we chose. So b is equal to the partial derivative of f with respect to y at x0, y0. Similarly, if you switch the rows of the variables around and look at the trace for y is equal to y0, you'll find out that a turns out to be the partial derivative of f z with respect to x at x0, y0. All right, so to recap here, we wrote an equation for just any given plane. And then we look at the trace of the surface, and then we solve for one of the two variables, and it turns out to be the same as the partial derivative. So the conclusion here with what we just did there, the plane tangent to z equal to x, f of x comma y at x0, y0, z0 is there we go. This equation gives us the tangent plane equation. So these partials coming here, and they make sense. If you throw one of these away, that's the slope of a line. If you throw this away, that's the slope of z with respect to y. Together here, this plane contains all the possible tangent lines, but the equation is found by using the two partial derivatives. And this extends to a higher number of variables too. For a three-variable function, let's say w is f of x, y, z. This is now a four-dimensional shape. We can't picture that, we can't sketch that, but we can still mathematically form a plane at that point. Now physically what that plane means is a different story, but we could do it. Okay, for a for three-variable function, now it becomes w minus w0 equal to fx, x0, y0, z0, x minus x0. The extension is exactly how you would expect. And if you keep going up with more variables, you just keep adding more stuff to it. The idea is the same. You're using the traces to find the slope, which is the same as partial derivative, and then put it all together to get a plane. Okay, let's try this on something. Z is equal to f of x, y. So two variable, three-dimensional. It's equal to square root of x squared plus y squared at the point 3, 4, 5. And we're going to find the equation of the tangent plane. Okay, first thing first, what shape is this? Close, not quite. It's not a sphere. What do you think? Use traces. Imagine y is equal to 0. Z is equal to the square root of x squared. So z is equal to plus and minus x. So these are two lines, right? The traces are two lines in each dimension. In the zx plane, you get two lines like that. In the zy plane, you also get two lines. So putting this all together, what do you get? You have this thing here revolved around, this thing revolved around. You get a cone. Yeah? Does that look like a cone? Yeah, close. I'll write it down, cone. There. All right, so it's a cone. It's not a sphere. A sphere, for this to work as a sphere, remember, sphere is x plus y squared equal to z squared is equal to a constant. There needs to be a constant somewhere for that to be a sphere. We don't have that. All right, so anyway, let's find the tangent plane at this particular point. So let's find the partials. Fx, this should be pretty easy to do. 1/2 x squared plus y squared to the minus 1/2 times 2x. So that's equal to x over radical x squared plus y squared. Partial with respect to y. There goes my microphone again. What's going on here? There. So partial with respect to y is exactly the same thing, with the x on the top replaced with a y. And we use the equation we just derived on the last page. The equation of the tangent plane is z minus the point equal to fx at that point plus fy at that point times y minus the y component of that point. Okay, so that's the equation we had in the blue box on the last page. And now we just need to evaluate these two functions at 3, 4. So this turns out to be, that's a 5 downstairs. That's a 3 over 5. This is a 4 over 5. And there we go. There's our equation of the tangent plane. Make sense? Questions? All right, so now let's use the tangent plane to estimate a point nearby that point, just like using the tangent line. Okay, keep in mind that that equation gives you the plane. Near the point 3, 4, 5, the surface z is equal to radical x squared plus y squared is roughly the same as the plane, which is, if I just isolate z, I get z is equal to 5 plus 3 over 5 x minus 3 plus 4 over 5 y minus 4. Okay, just like the first slide we saw earlier, you can replace that curve locally with a tangent line. Here we're replacing the surface locally with a plane. So in the analogy with people on Earth, this is the equation describing the surface of the Earth, a sphere, roughly a sphere. From our perspective, it looks flat. So from our perspective, it looks no different from this. Yeah, that's the same idea here. So for example, let's find out f at 3.01, comma 3.99. All right, so as a reminder, this is the equation we're dealing with. Let's first look at the true value of that z. The true value is you simply plug these into here. In our case, the true value is 4.99802. You have to use a calculator to find that, and I rounded at 5 decimals. The estimate from the tangent plane, we use this equation now with that x and that y. 5 plus 3 over 5. 3.01 minus 3 is 0.01 plus 4 over 5. 3.99 minus 4 is minus 0.01. And this turns out to be 4.998. Pretty close. And for all practical purposes, that's probably good enough. Yeah, the number is probably acceptable and perfectly good. Just like on Earth here, when you measure the distance you have traveled, you know in reality it's not a flat plane, but from our perspective, from our scale of motion here, it's about the same. The difference is very small. We're not going to be able to detect that. Same idea here. The change is so small that practically the plane gives us a good estimate of the true value. Make sense? Now, a couple names of stuff. Z is f of x comma y. And you've seen this when you did Calc 1. The differential of the function z is defined as dz equal to partial derivative with respect to x times dx. These are regular d's, not the funny-looking d's. Regular d, not that funny-looking d as in partial derivative. Okay, so that's a differential. And we actually use the differential in the calculation here. The differential gives you an estimate of how much z is changing. The estimated amount that z will change if x and y are changed. Let's take that previous example back again, and you'll see how this works. Okay, that same cone that we just dealt with. At x is equal to 3, y is equal to 4, z is equal to 5. Now suppose we don't know what the true value of z is. Let's say it this way, by how much will z change if x is now the same number we used earlier, 3.01, and y is now 3.99. And we know the answer already, but now we're looking at this from a slightly different perspective. Let's first work with a differential here. Okay, so here's our differential. fx and fy, we found them earlier. So there's our differential. dz is equal to x over square root of x squared plus y squared dx plus y over square root of x squared plus y squared dy. I'm sorry? This thing? No. Right, we have a 1/2, right? And then the chain rule gives us a 2, and then those go away. Whew, I thought I made a mistake. Good. All right, so that's our differential, right? Now, when we use the differential to estimate a change, dx, this is how much x will change. We're starting at 3, we're ending at 3.01. So the change is 3.01 minus 3, right? The new x minus the old x. So we change x by 0.01. Does that make sense? There goes my mic again. This mic is, what's going on? What about dy? What would dy be? We're starting at 4. We're going to 3.99. So dy is negative 0.01. It's the same as the regular change. These x and y refer to where you originally are, or the old x and y. And the reason why we use the old x and y is because that's where we form the tangent plane. We take the slope, the partial derivatives at that point, and then we flatten it out to estimate nearby points. So dx, dy, those refer to change, but the plane x, y refer to where the tangent line is built, always the old value. Okay, in our example here, dz is equal to 3 over 5, right? That's the partial at that point. 0.01 plus 4 over 5, negative 0.01. This part should look very, very familiar when we did a tangent plane. That's the part without the original 5. Let me point it out. Okay, so look, the tangent line here, 5 plus blah. This blah here, that's our differential. We actually use the differential when we're dealing with a tangent plane, stupid microphone, without calling it a differential. So that's the differential here, right here. And it turns out to be negative 0.002. So that's the estimate. By changing this little bit, how much z will change. This is equivalent to, by you walking a mile east, how much does the altitude change? We use the flat plane to estimate by making the tangent line on Earth, tangent plane on Earth, versus the real altitude change. The true change is the easy one. This is the z at the new x minus the z at the original x, y. Okay, so that's what the differential does. It's a rough change in the function in the presence of a small change in x and y. And of course, the same thing applies to higher dimensions. All right, now let me give you an example. This actually may come in handy when you're, for example, looking up a table of values. So this is where we interpolate table values. Let me bring back my heat index example again. It's a function of the air temperature and the humidity. And I'm just going to use a portion of this table. Okay, so this is just directly from the table I've shown earlier. It gives us the heat index in increments of 10 degrees and 5 degrees, and then increments of 10% humidity. So for example, you got this table here. You know, for example, the heat index at temperature 85, humidity 50 is 88. Now suppose we want something nearby that point, let's say 83, 49. That's clearly not something we have in that table. And you can kind of eyeball that and try to estimate that, but we can actually use our tangent plane idea to find the estimated change. So first thing is we find the closest value in the table. 83.49, so of course 85.50 is the closest. Okay, so we're going to base the change on the tangent plane using that point. And here I'm writing down the tangent line equation. And instead of x, y, z, we have capital I, we have capital T, we have lowercase h. But they're just variables. And these two, again, are the key values that we have to find. Without knowing what I looks like, we can't take the derivative. We can't do it. We only have these values here. So what do you think we can do to estimate these two partial derivatives? The average of the two slopes, right? Is that what you said? Yeah, exactly. Average of slopes near this point. So for example, if I want to know I sub t here, I'm going to find the change, the slope going from here to here, and then the slope going from here to here, and then average the two. So how does that work? For our example here, I sub t, average means you add up the two things and divide it by 2. So it's 1/2. Now first thing here, I want to know that, oh, there it is. First thing I want to know the slope going from 80/50 to 85/50. Okay, so that's going from the top value in column 2 to the second value in column 2. Later point minus the earlier point divided by the change in the temperature. That's just the slope. And then I'm going to add to it the second slope. So the point at the last point, 90/50, minus I at 85/50. And over changing t, I'm finding two slopes, a slope from one point to another, and then second to third, and then average the two. That's all I'm doing here. So this is equal to I of 85/50 is 88. I of 80/50 is 81 over change in temperature is 5. And then we have 96 over minus 88 over 5 again. So that's going to give me roughly, as far as the table can provide, the partial derivative. And this is 3/2. Similarly, for the other partial derivative, same idea. We get 0.2. Okay, now running out of time here. Before I upload the notes, I'll complete the rest of the steps. But then you would take these two, put into that equation, and use that to estimate the new heat index. So I'll complete the rest of this before I upload. All right? All right, that's it. See you Wednesday. That would be a tangent space.